Okay, here we go. Last lab. Hopefully you've been learning some stuff along the way. Hopefully these things have been informative for you. The last lab is based on amplifiers. When I told Dr. Alexandrov we do amplifiers in the lab, his thing is making devices, making the technology that goes into making integrated circuits and transistors. So when he thinks about amplifiers, he thinks about transistors. You're going to take a lot of awful stuff. But in the lab, we use what we call operational amplifiers. And it makes it way easier, okay? So the first thing we want to do is kind of introduce you to the device. And anytime you're using a device or even transistors and that, the main thing you got to do is get the data sheet for the device. So you look it up online, you download the PDF, and you take a look at the device and all of its characteristics. And it gives you sample circuits and things like that to help you through. But the very first thing it'll go through is the pinout of the device. Because what we're going to do, and I'll show you in the demonstration, we use integrated circuits, ICs, right? And they're going to look like this. Right? So it's going to have 8 pins on the IC. The very first thing you want to do is find out which is pin number 1. Normally there's different denotations depending on the manufacturer. It could be a dot like this. It could have a little cup, or it could have a bar, or it could be a combination of any of the above. Okay? And that says that this is pin number 1, 2, 3, 4, 5, 6, 7, and 8. Okay? It numbers it around in a horseshoe. Okay? And then usually what it does is it shows you the connections to the device. So I'm just going to get rid of these things here. Okay? And the amplifier is a little triangle. And it'll look like this. Okay? We have 2 inputs, and I'll draw this a little larger. Well, actually, here, I'll draw it a little larger right now. We have 2 inputs, okay? The negative says it's an inverting input. And then the positive is the non-inverting input. And depending on how you use the amplifier, you might use one or both of these different inputs, and then this is your output. Okay? So, simply an amplifier, right? We put in a small signal, we get a bigger signal out. And that's what we want to do, right? Well, actually, but there's a lot of different applications for these amplifiers. I'm going to go through a couple of them that aren't just amplifying, but we'll cover those in the 3rd and 4th circuit. Okay, so we have our 2 different inputs and we're going to put a signal in, we're going to get a bigger signal out. Okay, so let's do our first circuit then. Okay, so here's our first circuit. We have our input signal coming in. It's fed into the inverting input, and we're going to get an output. Okay, so when we feed the signal into the inverting input, this is called our inverting amplifier. Okay, so when we put we're going to put a sine wave in, and we'll get a sine wave out, but it'll be 180 degrees shifted, right, or inverted. Okay, and the other thing we want to do when we design amplifiers is we want to control the gain of the amplifier. Like, how much bigger are we going to make the output compared to the input? And with these operational amplifiers, it's really simple, okay? So we say that the voltage gain, AV, right, so this voltage equals minus RF over RI, okay? So RF is the feedback resistor. It's feeding some of the output back to this, and this is our input resistor here, okay? So depending on the combination of these resistances, we can make it bigger, 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 or smaller. I mean, we could remember our potentiometer from lab 2, we could use one of those to have like a variable gain, okay? But in our case, we're just going to stick with a straight single gain, okay? So for this lab, and also this negative sign doesn't mean subtraction. It just means that it's inverted, okay? So that's just denoting the inversion, okay? So for our example, we use a 3.3K and a 1K, so we should get 3.3 over 1, right? A gain of 3.3. So say, for example, we have our input signal, and say it's 1 volt and minus 1 volt. Okay, so 2 volts peak to peak, but 1 volt peak. Okay, so when on the output, what we should get is a signal that's 3 times larger but inverted. Okay, so it's going to look something like this, right? And plus 3.3. Okay, so that's what we expect to get out of here. Okay, so and then what I'd like to do is kind of run through another little example here. So what we have then now, if we increase the input, say we made this 10 volts now, and now we're expecting 33 volts to come out. Well, that doesn't happen. Okay, so one of the other things that I showed you, or I haven't showed you, sorry, is that these amplifiers have power supplies. They run off of voltage. And actually, I erased the IC. This is going to be pin 7 for the plus voltage. And then this is going to be minus V down here. This is pin number 4. Okay? So on the IC, like, these would be the different connections. And then what we do is we're powering it with plus and minus 12 volts, right? So this is going to be plus 12, minus 12. So the maximum voltage we can get out is 12 volts. Or actually, it can't get quite to 12 volts. So what ends up happening is it comes up here like this, and then we say that the top gets clipped off. This is called clipping distortion, right? Right? So say if you were doing this on your amplifier, right? You're at home, you're listening to AC/DC, you want to crank it right up. And then you crank it up and it sounds really raunchy and crazy. Well, actually it's getting distorted, right? Because what you've done is you're clipping the signal off, right? And it might sound better, but I'll tell you something, it's not better, because what ends up happening is you fry your speakers by doing this. And it's not because it's too loud, it's because the main component of your speaker, the speaker itself, has what they call a voice coil, right? And a coil essentially is inductor, right? And you took that in the class. And when you get this flat portion here, the flat portion is now DC. The frequency is 0, which means the impedance of the speaker goes to 0, because XL equals 2 pi FL, and F is 0. So now you basically created a short circuit condition on with your speaker, and it pulls a lot of current through it, and it'll kill your speaker, right? So that's what you do. Buy a big kick-ass amplifier so you can crank it up as much as possible, and you don't get the clipping. But the other problem is you don't get that distortion, and then, I mean, I got buddies that come out and they listen to my big stereo and they go, well, it's kind of loud. Well, it's way louder than yours, but it's not distorted, so it doesn't get that really harsh sound, so they're disappointed, but whatever. Okay? So anyway, so this is our first circuit. Okay? And like I say, I'm going to go through, I'll tell you a little more about it when we do the demonstration. All right? Okay, so let's go to the second circuit. Okay, so now in this case, our input signal is going into the non-inverting input. So this is our non-inverting amplifier. Okay, and now the gain of this okay, so with the non-inverting amplifier, it is possible to actually make the signal smaller or attenuate the signal. But in this case, you have this +1, so it's always going to be an amplifier. It's always going to make the signal bigger, right? So, and in this case, we're going to use 2.2K. This is going to be 1K again, right? So this is going to be 2.2 over 1 plus 1, so, okay? So the gain is going to be 3.2, so it's almost the same gain, amplitude-wise, as the non-inverting. But in our case now, this one, right? If this is our input signal, our output signal is going to look like this, okay? So if this is 1, this is 3.2, but it's in phase, right? So it's not inverted compared to our input, okay? So a lot of times, most times, like when I design these circuits, I always use the inverting amplifier. And then if I need it inverted back to a normal, I do that. Because a lot of times, the non-inverting circuitry, it gets a lot more complicated, okay? And I'm just going to say that. And the non-inverting, or the inverting amplifiers, they keep it kind of simple. So most of our applications will be using like an inverted input. But it is possible to make a non-inverting. Okay? Okay, so that's our second circuit. Okay, so our third circuit, and again, I'm just going to, if you look at the lab manual, there's other circuits there, little more elaborate circuits to actually make things function well. I'm going to give you the quick and easy circuit. Okay, so what we have here, okay, so here we have our, this circuit is called a differentiator. Okay, and what we see, we have a capacitor on the input, okay, and again, like with all the other circuits that we kind of looked at that use capacitors, when you have capacitance or inductance, you're going to have frequency ranges where the circuit acts in a certain way, and other frequency ranges where it's not going to operate the way you want it to. Okay? So what we have to do is design these circuits, and again, in the lab manual, there's equations for how to calculate these different things. I'm going to just go through the kind of the overall theoretical, not so much the theoretical, but the practical applications of these and what happens, right? But we size these components to operate within a certain frequency range. And again, when I'll do the demonstration, I'll kind of go through a little bit more of this, okay? But, so again, what we have, when we have a capacitor, it's going to have a certain frequency range, okay? And the other thing it's going to do, the differentiator is going to take the derivative of the signal, right? So it takes the derivative of the signal. So what I'm going to do is I'm going to feed in these different waveforms and see what if it's the derivative of the signal, okay? So what's a derivative, right? The derivative is the rate of change. So when we look at our signal, we have to figure, okay, what's the rate of change of the input? And then what should the output look like? Okay, so we're going to do these three different waveforms, right? We're going to do our square wave. We're going to do a triangle wave. And we're going to do a sine wave. Okay? So, again, when we look at the waveform, what's the rate of change of this? Right? The rate of change of this is 0, right? It's not changing. Okay? And then what's the rate of this? This is infinite, right? That's an infinite rate. Well, actually, the way I draw it, it's not infinite, but that's supposed to be a square wave. Okay? So it's infinite. So what we should get out of here is 0. And then we should get a spike like this. And I'm going to draw it like this because it actually is the capacitor, the RC is creating this. Okay? So you should get a spike like that. And then a negative spike like that. That's the derivative of this. Okay? But say if we were inside or outside of the frequency range that it works at. Right? So if this, okay, right, this is our RC, right? It's charging and discharging. I mean, it's all the same theory, right? And remember our tau, see how our tau is going to be very short compared to the overall period of the waveform. Okay? But say, for example, our tau was larger or our frequency was faster, right? So the frequency gets fast, so it doesn't have, so it might actually look like this. Right? And so that isn't the derivative of this. Which means we're outside of the frequency range that this circuit operates at. Okay? Okay, so let's move to the triangle wave now, right? So the rate of change of this, right? This is essentially mx plus b, right? This is like, well, minus mx plus b, the negative slope, right? So what, and the derivative of that is just a constant, right? So this would be a positive constant, a negative constant. So what we should get is a square wave out. And then for our sine wave, and the one that everyone remembers because you take all these trigonometric identities, right, is, well, it should be minus cosine. Or sorry, no, it's positive cosine. Right? And that's supposed to be a cosine wave. Okay? And again, I'll go through and I'm going to demonstrate these different, with these different waveforms, and I'll change the frequency, and I'll show you when it's out of the frequency range and when it's in the frequency range, and I'll show you those things. Okay? And then our last circuit is going to look like this. Okay, so, and then one other thing I should mention, again, we're using the inverting input of this. So when I said that the sine wave, the derivative of that is cosine, well, when you see it in the demonstration, it's actually going to be minus cosine because it's going to be an inverted circuit. Again, if you had the non-inverting circuitry, it becomes way more elaborate and it's way more difficult to deal with. Okay, so now the capacitor is in the feedback loop. Okay, this is going to be our integrator. Okay, so the integrator takes the integral of the waveform. Now again, what we're going to do is we're going to put in our different waveforms, right? Try these little. Okay, so the integral is the area under the curve, right? And the area under the curve, in our case for the square wave, is increasing linearly along here, right? So that's y equals mx plus b, right? So if this is a positive area, right, we get the positive. So what we end up doing is getting a triangular wave out. Okay, so now let's say it's outside of the frequency range that it works at. Okay, one of the things we're doing here for these circuits, when we charge the capacitor, the very initial charge, right, starts charging rapidly, but it also is fairly linear. So when we use these things, this is just a very early part of the charge of the capacitor, so it's linear. So if we were to say use a slower frequency, what we might see is it might look something like this. Right? And like that's not what we want. So one of the things that happens too, and especially like with this integrator, we're using just that initial charge, so the output, in order to make it look triangular, gets attenuated quite a bit, right? Because we're just using that first little bit of charge. So again, all these, there's a lot of little stuff that we're kind of not covering here because again, you guys are not electrical engineers. You're not going to be designing these things, but you're going to be using them though. And after I'm done this, I'm going to tell you where you're going to use them, right? Okay? So the next one is kind of cool, right? I mean, we use these things for more than just amplifier, like to do the derivative. Like what are you going to use the derivative for? Or what are you going to use the integral for? Well, again, I'll give you an application in a minute, okay? But one of the other things you can do is you're changing the shape of the waveform. So when you use like your function generator, or say you needed to use a certain shape of waveform, you can create these different shapes using circuits like this. Okay? So now when we look at the triangle, right, this is mx plus b. So the integral of that, right, is going to be x squared, like parabolic. But what ends up happening here is it kind of ends up looking like this, right? So we've taken a triangle wave and changed it into a sine wave. We've taken a square wave, we changed it into a triangle wave. So we've shaped our waveforms with these different circuits. Okay? And then integral sine is minus cosine. And again, so I'm going to go and I'm going to demonstrate all of these things, right? But then again, now why are we taking all this stuff, right? Now, again, depending on the discipline you're in, like if you're in chemistry or mechanical, software, you'll probably doing some of this stuff too. Civils don't do it, you miss out, or well, maybe that's a good thing, right? But what these are for is in your next year, you're going to take a course called control systems. And in control systems, the main way to control a process is they use a PID controller. Right? Proportional, integral, and derivative. Okay? And that's all of these different circuits, right? The proportional would be the inverting or the non-inverting. the derivative is the differentiator, and this is the integrator. So you put these things together and you can use them as the process control circuitry. And then when you're tuning your controller, and you're going to have fun doing that, you're going to be changing the parameters of the integrator, differentiator, and the proportional to make your system function in a certain way. Okay? And so one of the number one way of tuning your controller, which isn't always the best way, again, it depends on your application, they call it quarter amplitude decay, right? So if this is our set point here, right, we want to get to this set point as quickly as possible. And what they say is the fastest way to do that is use this quarter amplitude decay, and the response looks something like this, right? Right? So the integrator here, or sorry, the proportional is primarily giving this. The derivative can have some effect here as well. And then when you cycle around your set point here, right? Like this one here is supposed to be 1/4 the size of this, right? That's the quarter amplitude decay. And what gets rid of that is your integrator, your area under the curve, right? So again, you're using all of these circuits to come up with a process control. And that's what you're going to be doing in your control systems course. And we do these circuits so you have some idea what you're dealing with when you are tuning these controllers. Okay. Okay, so that's all I've got to say about this. Hopefully you've learned a lot from this and it's helped you to actually understand the theory that you're taking in the class. Again, I'm going to be doing the demonstration later. And yeah, that's it for 2151 labs, okay? So I'll meet you in the lab and we'll go through our demonstration. Okay, thank you. Okay, here we go. This is a demonstration for lab number 5. Again, hopefully you can see this is getting kind of cluttered here. But here, this is what we call a breadboard. And we can assemble our circuits on here. Basically the IC, here's our IC, right? Remember it has 8 legs, you can kind of see that. And it straddles the center, so there's no connection in between this side and this side. But all of these lines are connected together here. So if I plug my IC in here, you can see this one yellow wire is plugged in the same spot as this pin. So they're making a connection. And then it's coming down to the minus 12 volts here. There's my plus 12 volt connection here. That's pin 4 and 7. And then you see our connections to pins 2 and 3. And oh, we're missing a connection there. I don't know who wired this one up. I had some grad students were helping me. I'm sure it's obviously their fault, right? Okay, I'll take care of that. Okay, but so here we go. This is our first circuit here. And we can see our yellow line is our input voltage, and it is 6.2 volts peak to peak. And then our output is the green waveform, and it should be 3.3 times higher, right? Because we had RF is 3.3 and RI is 1K. So that gives us a gain of 3.3, and it should be inverted. And a 6.2 is the input, and 20 volts even is the output. Okay, so 6.2 times, that's 18, it's 19. So it's pretty close. Okay, so then if we move to the next circuit, which doesn't have a ground connection on the input, here, I just grabbed this crazy looking thing here. I hope this is actually going to work here. And this, yeah, so this goes here. Okay, so now I'll move my, that's why it's not, that's not ground. The input is the ground. Okay, so now we're going to move this over here. So there was nothing wrong with the circuit, so I must have wired it up. Insert my, okay, and then we'll move this to the output on pin 6. Okay, so now we see, again, okay, so the output has gone up a little bit. It's 6.7 volts. And see, and again, that's one of those, the loading effect, the voltage regulation we did in the last lab. Because the impedance of this circuit has changed, that means the source is not getting loaded down as much. So it's 6.7 input and 20.7 output. So again, it should be, because it's 2.2K plus 1, so 2.2 plus, so 3.2 should be the gain. And as you can see, it's in phase with the input. Okay, so now we'll move to the differentiator. And so what I'm going to do, okay, so I'm going to move this over. And remember, this is where we're going to put the different shaped waveforms in, right? So let's start with our square wave. Okay? So as you can see here, things aren't looking very good, right? So we're not operating within the proper frequency range. And if you did the design, like if you used the equations in the lab manual and you did all the calculations, what you're going to find out is that these are made to operate at a very low frequency. So if let's drop this frequency down here. Where did that not go? Okay. Okay, and what I'll do is I'll shut off the input. Okay, and I mean, this is really hard to see. But you can see there's like these little spikes here, right? And that's what we want to see. That's the derivative of a square wave input. Okay? So then if we change to our triangle wave, the triangle wave should be a square wave output. Okay? And again, it's very attenuated. But you can see that's like very square. We're at 70 hertz, right? So very low frequency. Okay? And then what we want to do is go to our sine wave. And then I'll put my input waveform back on, and you can see right? So when it's and again, it's a negative input, so at the zero cross, so it's minus cos coming out, but again, because it's an inverting waveform circuit, it is actually cosine coming out. So again, so when we're using these circuits, you have to design them for a certain frequency. And these ones were designed to be operating at a very low frequency. Okay, so now we go to the integrator, and the integrator can be kind of tough because the capacitor and the feedback can sometimes charge up. So we'll see what we can do about capturing a waveform here. Okay, so we'll move this over. See, and it's already gone. Okay, so let's move this to our square wave. And it disappears really quick. So what I'm going to try and do is I'm going to try and okay, never mind. Okay, so here we go. We can, I'm going to turn down the amplitude. It looks like it's clipping here. Okay, so actually this is actually, okay, it was just, had a big gain on it, and we couldn't see the, okay, now, so the square wave, here's the square wave input, and we get our triangle wave output, and that's what we should be getting. There's a little glitch up here, and that's probably just, again, a bit of a wiring issue here. So it's not a big deal. But actually, that's actually working quite well. Okay, so then if we go to the triangle wave, we should get a sine wave out. And here, let me just, okay? And you can see, like there's my triangle wave input, and then there's my sinusoid. It's a little rounded compared to what a normal sinusoid would be, but I mean, it's actually pretty good. Okay, and then we'll go to our sine wave. Here, I'll stop this. Okay, and again, this should be minus cosine, but again, because it's an inverting amplifier, at the zero cross, it starts at the positive and comes back, so it's actually showing cosine. But again, that's because we have an inverting circuit. And again, really, so what I would do, so if I had a PID controller, if that's what we were going for here, I'd have my proportional, my integral, and my derivative, and if they're all inverted, the other thing we can do, other amplifier setup we can use is called a summing amp, and so you would add those three together to give you your final output of the controller. And when you add those together, if you added those together through another inverting amplifier circuit, you got your proper output and everything is good. All right, so anyway, that is it for 2151 Labs. Again, hopefully you learned a lot, and this is going to give you enough information and help you through your course load. And I'll expect your lab reports in, and we'll, if you're signed up for the class and I see that you're lacking some marks, I'm going to email you and start bugging you about handing in your lab reports. So get these guys in, get them done, and otherwise we'll be doing this again next year. Okay? Okay, so thank you, and good luck on your finals. Bye.